So our topic today is atomic theory and structure, and by the end of this presentation you should be able to answer the following questions. Question number 1, based on the experimental results, match the scientists with the subatomic particle that they discovered. For example, Dalton, Rutherford, Thomson, and Bohr. Number 2, explain how you would calculate the average atomic mass of the element when given the percent abundance of the isotopes. And number 3, distinguish between the structures of a neutral atom, an isotope, and an ion. Okay, so here we have the progression of the atomic theory, and this is basically the history of the atom and how the atom progressed, the different models progressed based on the amount of technology available to the scientists at the time. Our first scientist is John Dalton. John Dalton proposed a modern atomic model based on his experimentation, and he came up with Dalton's postulates. His postulates stated that all matter is made of atoms. Atoms of an element are identical. Each element has different atoms. Atoms of different elements combine in constant ratios to form compounds, and atoms are rearranged in reactions. Our second scientist is J.J. Thomson, and in 1897 J.J. Thomson used the cathode ray tube to determine that there were electrons present, or negatively charged particles. And the way that he did that is he used the cathode ray tube, and he had a power source that he ran through this contraption, and he had a negative end and a positive end, and he ran a stream of energy or electricity through this tube, and he positioned a positive plate and a negative plate, and based on the attraction then he would be able to determine if this stream of energy was positively charged or negatively charged, because like in magnets, the negatives would be attracted to the positives and positives would be attracted to negatives. So this bend in the light upwards towards the positive plate told Thomson that there was a negatively charged particle in this stream of energy. Based on that experiment, J.J. Thomson came up with the plum pudding model, which said that basically we have electrons embedded in this positive pudding. So there's just a bunch of positive matter, and every so often you find an electron or negative embedded in there. So he believed that the electrons were like plums embedded in a positively charged pudding and called it the plum pudding model. Our next scientist, Ernest Rutherford, had a gold foil experiment where he took the alpha particle and shot it through a piece of gold foil. He needed a pure substance so that he knew that everything in the foil was made up of gold particles, and so he shot a piece of light, alpha particle, through the foil, and he used this detection screen to determine where the light went. Sometimes the light would go straight through out on the other side. Sometimes it would be shot either to the right or to the left from the middle, and then sometimes it even was deflected and came back to the back of the screen. Here's a side view of the gold foil, so it's looking at this side of it, and you can see what was happening is sometimes it would go through the particles of gold, not hitting anything. Sometimes it would hit something and be deflected back. Sometimes it would hit something and be deflected either to the right or to the left. His conclusions based on this experiment, he said that the nucleus is small, the nucleus is dense, and that it was positively charged. Okay, and here this scale represents the mass of a neutron and a proton. So a neutron and a proton, their masses are almost equal to each other, and these two particles make up the nucleus of an atom, and the nucleus of the atom is responsible for most of the weight of the atom. Over here we have a balance that shows a proton 1 proton and 1,830 electrons. So it takes a lot of electrons to equal the mass of 1 proton. Therefore, the mass of electron is negligible or not even really there. It doesn't contribute to the overall mass of the atom. So the mass comes from the proton and the neutron, or the nucleus of the atom. Okay, our next scientist is Niels Bohr, and he came up with the atomic model, and sometimes it's referred to as the planetary model, where it has the nucleus made up of the protons and the neutrons, and the electrons orbit in shells around the nucleus. So we have the protons and the neutrons in the middle in the nucleus, and then around the outside we have the electrons in different energy shells. So here is what we would call Bohr model, and this is how we would represent an atom. We have the nucleus in the middle, and then we have energy levels or shells, and each shell is represented by an N, and this tells us how many electrons can occupy each energy level. So the first energy level can only hold a maximum of 2 electrons. So here we have 2 electrons. And the second energy level can hold 8 electrons, and so on and so forth. So that the further you get away from the nucleus, the more electrons that energy level or shell can hold. Okay, atomic number and atomic mass. Elements are often symbolized by their mass number and their atomic number. So here we have oxygen, and these values are given to you on the periodic table. The number at the top is the A number. The A number represents the mass number, and the bottom number is the Z number, which is the atomic number. So the Z number is the number of protons, or the atomic number, and the A number is the mass number, which is the protons plus the neutrons and the protons, or the atomic number and the neutrons. So given these numbers, we're able to find out the number of protons, neutrons, and electrons. So in oxygen, to find the number of protons, we look at the atomic number, or the Z number. So for oxygen, we have 8 protons. The number of protons is also equal to the number of electrons in a neutral atom, so we have 8 electrons. And our number of neutrons is equal to the mass number, or the A number, minus the atomic number, or the Z number. So if we take the A number minus the Z number, so in this case 16 minus 8 gives us 8 neutrons. Okay, this information, this is how it's going to be given to you on your periodic table. You're going to have a number at the top. This represents the atomic number, or the Z number. And here we have the atomic mass, or the A number. And so when you rewrite it, you're going to write the A number on top. So in this case it's 4, and the Z number on bottom. So for this helium, the number of protons, neutrons, and electrons. We use the Z number to tell us protons, so we have 2 protons. The number of protons equals the number of electrons in a neutral atom, so we have 2 electrons. And the number of neutrons is the A number minus the Z number, which gives us 2 neutrons. So we have 2 protons, 2 neutrons, and 2 electrons. Okay, now let's talk about isotopes. Isotopes are atoms of the same element that have different numbers of neutrons. So you have 2 versions of helium. You have a helium with 1 neutron. Neutrons are represented by the turquoise. And then you have a helium with 2 neutrons. Same thing for lithium. Here you have 3 neutrons. In this lithium you have 4 neutrons. So same element, just a different number of neutrons. We have a certain way to write our isotopes. We use the name of the element, a dash, and the mass number after it. So this is carbon 12, meaning that the mass number of that particular version of carbon is 12. This carbon, though it's still carbon, has more neutrons in the nucleus, so it's carbon 14. And here's uranium 235. Okay, the way that we're going to use these isotopes is we're going to be able to calculate the average atomic mass of an element. And this is based on the percent abundance of each variety of that element in nature. And so we're going to use this formula. For each isotope, we're going to find the mass of that element times the percent it is found plus the second isotope, mass and the percent, and then the third isotope, so on and so forth. So let's do an example. Calculate the average atomic mass of lithium, which occurs as 2 isotopes that have the following atomic masses in abundance in nature. So our first isotope is of lithium is 6.017 AMUs. Its percent abundance is 7.30%, and the second form of lithium has an atomic mass of 7.018 AMUs, and its percent abundance is 92.70%. So using our formula, I'm going to take our first mass, and we are going to take 6.017, and we are going to multiply that times our percent, but we're going to convert the percent to a decimal. And then we're going to do the same thing for our second isotope. And we are going to take the 7.018 and we're going to multiply that by the decimal form of the percent abundance, which is 0.9270. When we do our calculations, this times this equals 0.4392 plus this times this equals 6.5057. And then when we add these two numbers together, we end up with 6.95 AMUs. Make sure when you record your answer you use the correct number of significant figures. Okay, our last topic are ions. Ions are atoms, and they have either gained or lost their electrons. Metals that lose their electrons are called cations. Nonmetals that gain electrons are called anions. And one thing to note that's very important is atoms can only gain or lose electrons in their valence shell. So their valence electrons. So this, on the outside energy level, is a valence electron. So it's only going to lose that one electron. Okay, to write ions, since electrons are negatively charged, when elements lose an electron, it becomes positive, or if it gains, it becomes negative. So for example, if I have a calcium ion, a calcium ion is going to be represented this way because it has gained 2 electrons, or it has 2 more positives than it did negatives. So it's, it has lost 2 electrons. So this has lost 2 electrons, or it has 2 more positives than negatives because it has now lost 2 electrons. Or you could have chlorine. It is written this way. This is saying it has gained 1 electron, meaning that it has 1 more negative than it does positive. So it has gained 1 electron. And you can leave the 1 off here and just show it as an imaginary 1 and do just the negative sign. So here another example would be potassium. A potassium ion lost 1 electron. Because it is now positive by 1, so it lost an electron, it has 1 more proton than electron. Or sulfur gained 2 electrons, meaning that it has 2 more negatives than it does positive. So when you see the plus here, it means it lost, and when you see the negative here, it means it gained. Okay, so now at the end of the presentation, if you cannot answer the questions from the beginning of the presentation, you'll need to watch it again.